You only record once.
Hello. We are live with our CEO, Jonathan Berry. Hey, John. Thank you for
Hey, how's it
joining.
going?
First time on the hardware stream. You always just go to these IoT streams. And a late riser, Mr. Dan Mangum.
I always get up late.
Yeah. What, today was 5 instead of 4 a.m.?
Right. Oh wow, I don't have my nicer camera set up,
Your
and so you
fancy
really
cam.
get the
I
full
was
experience of my office.
What I'm
right
seeing
now.
is all the boxes that I have stored at your house.
Yeah, right.
I miss you, hardware. Come back to me. Maybe tomorrow. Dan has my stuff hostage, and it's very much appreciated.
Is it good stuff or is it stuff you wanted
Oh,
to?
it's good stuff.
Yeah, it's good stuff.
It's nice. It's like nice test equipment. It's like basically all the stuff I didn't want to put into a storage container when I was moving, which is the context for people there. And it's at Dan's house, though.
It's like the Fort Knox of test equipment.
There we
Pure
go.
and reliable storage.
Yeah, exactly.
How about
Okay,
your new camera setup here, Chris?
My
I
new
don't know if you know this, but every person that I talk to at Goliath during the week, we always spend about 5 minutes talking about how good your camera looks in your demos now.
Well, what can I say? New camera, just like the old camera. This is the one I had before, but now I have a nice big window in front of me and a big old light. Just the
Always
usual,
the lighting.
I don't know. Yep. I actually have thought about upgrading my camera again, and I just have to like slap myself every single time because I'm like, this thing never moves. I don't need any features more than like camera sits here and does nothing.
Right.
So
No, while you're in the middle of moving, you were using your DJI cam.
yeah, that thing's pretty good.
Yeah,
The
that's pretty good.
Pocket,
I was like
Pocket
surprised.
3. Yeah.
Yeah.
That thing's, I mean, it's a 4K camera with a little gimbal on it. So that's now been downgraded to down camera, but we don't have any hardware to look at here yet. So we will just be looking at renders for now.
No extra camera needed.
Yep. Okay. Well, speaking of hardware, let's get some on screen, huh? Share screen. I'm going to share this entire screen. Let's do a quick recap on where we are. So the Dram project, also said Drachm by some, is rapidly approaching a first board being done. And this is the Dram 1 has a 9150, sorry, excuse me, NRF 9151, which is one of the new modules from Nordic that is set to be released sometime in this quarter, I believe. It has an ESP32C3 on it. It's got an ATEX 608B. It's got a 4 megabyte memory unit. It's got a bunch of supporting cast in terms of RF stuff. And it actually has layers. And it actually, well, I guess since the last time I recorded, it has this big silver fence around the outside. And this actually came from the idea of like, well, what if we actually made this thing and someone wanted to take it to production and design something with it? The answer is they probably would not have a good time at FCC testing without an RF shield over it, because I mean, basically, if you look at the ESP32C3, those are almost always in modules. They're pre-certified, whatever. And so we'd want to kind of replicate that idea here. And we want to carry it again through to Dram 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Should I keep going?
How much RAM does your computer have?
Yeah. Well, and actually, that's a good point. Actually, one of the big problems that's going to happen today, I can show here. So I'm like getting down to the end of this, and I don't have many rat's nests remaining, right? Because I've like connected this all up, and I'm really excited about that. And then I go to like check down here the unrouted, and I see, oh my God, I have 448 unrouted connections. And that's because, of course, I do. I have just like a bunch of boards here that are not connected. And so that's actually going to make it really tough for troubleshooting and DRC and ERC like we talked about today. So I'm probably going to delete the other boards and maybe make this a separate repo. I don't know quite how to do that. I mean, I want to have like a kind of common repo, but also then like a finished repo, because when you think about it, like these are all of these are actually running the same ground plane as well. So this is probably an inadvisable way to do KiCad layouts generally, and with multiple boards and stuff like that, unless you're going to put them all in the same design. It's just you kind of have to be done with everything before you can send it out. So yeah, we'll probably be deleting a bunch of stuff today too. So that'll be fun.
Does KiCad have a concept of like assemblies?
If I know.
If you don't know, then we're screwed.
Yeah. That actually used to be one of my favorite Muppet jokes. What do you get if you combine a rhinoceros and an elephant? Elefino. It was said by that little shrimp character too that I never understood. But
your accent, you knew it right away. I think he's he's from like Louisiana or something.
Yeah, he's like yeah, exactly. Except like, would you want to be a shrimp from Louisiana? That'd just be like very dangerous.
I think it's the whole point.
Yeah. Good old Muppets.
He left the gumbo.
That's right. Okay, so so today we're going to be doing error checking. We're going to do design rule checking, which is basically, does this thing conform to what we expect it to? And then if it does, then we could, I guess, push it to, could even upload it to a PCB manufacturer if you really wanted to. But I don't know if we'll actually do that. So let's start with questions from both of you. Any questions?
I'm admittedly a little behind on catching up on the streams.
It's okay. It's only an hour and a half every week in six different sessions now.
Right. Well, so you mentioned the kind of like border you put on there. Can you talk a little bit more about what that is and maybe like what the properties of it are, like going into a little more depth on it?
Sure. So imagine you're it's like trying to keep the crazy in, right? Let me pause my notifications real quick.
I have a prop. I'll get a prop if you need one.
Okay. Yes, and actually, there's a good prop right next to it. So over here, this is the Dram 2, and this is a BG97 with a NRF 52840. Right, that's kind of the next incarnation we'd like to try out, and that would basically be the NRF 52840 Bluetooth chip as the controller, and then it uses the Zephyr subsystem for the BG95 or the BG77. They're the same modem, just in different form factors, or the same chipset from Qualcomm in different form factors. And the idea being that that is also a module, right? And you can kind of see it in this 3D render. Is basically a PCB with a metal shield over it. The idea being that you only want the RF signals to come out. Oh, let's see what John's doing here.
I'm just holding up a ESP module.
ESP modules are also a good example. Anytime you see a metal can, though, usually what that means is the manufacturer is taking it through pre-certification for you and doing it so that you don't have to do as much at certification time with the FCC. And so regardless of when you do this sort of thing, you are going to have to kind of keep the RF signals keep the RF signals going where you want them to go. So in terms of the, you have controlled impedance lines going out to a U.FL connector in this case, over here, right? But you don't want the errant RF from discontinuities and just poorly matched impedance lines to be radiating elsewhere. If they do radiate, you want to basically capture them with a ground cover, absorb them, and give them a nice return path. I feel like my camera is slowing down here. Not sure if the video is slowing down.
Looks good to us.
Okay, great. And so, yeah, so basically you think about it like, say the 2.4 gigahertz signal is coming down this controlled impedance line here, and it catches just like
You're
a
not.
corner.
I'm not seeing your screen.
Oh, yeah. Thank you. So say it's traveling down this path here, and it catches a corner, and there's like a small reflection, and then that causes it to radiate 2.4 gigahertz energy, right? Normally, it just would kind of radiate in all directions until it dissipates. But if it finds a ground return path, in this case a shield, so if this is the point of radiation, it's kind of radiating out this way, and you have a cover that's a ground return path, then it's going to hit that and return to home, kind of thing. So the idea being that you kind of encapsulate this whole thing in a ground plane biodome, effectively, and you give Pauly Shore a place to live. Is that a relevant reference?
That is probably the best explanation I've ever had around shielding.
Biodome, classic.
Another thing I'll kind of like at the higher level. This dev board from Espresso, this is an Adafruit dev board, is not FCC certified. The module is FCC certified, and so actually you can't see this on because my camera's awful. But there's an FCC ID on this module that the Adafruit's using, and it's because they put that canon and they went through that certification. This board probably couldn't pass FCC certification. It's borderline because there's no additional RF stuff, but like who knows? And so effectively, I'm never gonna forget this Pauly Shore reference. The way I was taught it was like, you want all the RF to go to one place, which is the antenna and only the antenna. And so you put this thing to kind of like shush it to the antenna.
Shush it, give it a little shush, huh?
So in this case, though, we have modules on the board already that have a CAN over them. So we're putting like a CAN over a CAN, sort of.
Yes, that is the non-standard part of this, right? So, and this is a design of my own making. Basically, I would go to a RF shield manufacturer, basically just bent metal, and give them the spec and say, hey, can you bend this for me? And then that would get put into a tape, put down, mounted to this thing. And then you have, you'd open up your solder paste stencil around the edge here to also have paste at assembly time and stick it on there, do reflow, that sort of thing.
So
Nice.
is it correct to then assume like these shields they're not like RF voodoo, like the antenna or the other analog stuff, and so like you could literally have 10 shields if you wanted to for no good reason?
Yeah, like a nesting doll of RF grounds.
If we put a shield over the, I don't know if any of these have an ESP module, it won't have any impact on its performance one way or another if you have more than one shield.
No, so one thing about that though, so like the one that John showed actually had an integrated antenna, right? So if you had a ESP32 with an integrated antenna, and then you put a metal shield over top of that thing, it's just going to absorb all the energy that is coming off the PCB. A PCB antenna in that module, right? So if you put a shield over top of the shield plus PCB antenna, then you're basically just, basically you're making a Faraday cage around that PCB antenna, and probably not all, but a good chunk of your RF energy that you're trying to actually put out will get absorbed, and that would be a bad design.
Mm-hmm. So if this board had a UFL connector instead, and you routed the wire from the antenna outside of the shield, then potentially it'd have less impact.
Yeah, I mean, generally, I think it's just so like this is showing a metal shield on top of the cellular component here, but it's still it is asking you to route the RF out of a pin on this one, right? So there is no built-in antenna on these cellular modules because one, you can't really fit a cellular antenna in the space provided, right? The PCB antennas for cellular are rare because of the higher requirements. It's not just an inverted F copper antenna on PCB material. So usually it's just kind of to catch all of the extra, it's not just actually RF energy either. It's also clocks, high speed signaling, things like that. Every time you have a square wave that is, so this thing's running, I think I don't know what this is running at, maybe 96 megahertz. whatever this is getting clocked at, right? So say, let's just say 100 megahertz for ease of use, right? Then you start having multiples of those frequencies because of how square waves work. So when you're clocking at 100 megahertz, you could see frequencies of gigahertz, the 10th. Oh, my brain's not working today. Need more coffee. The 10th harmonic might have a spike. And so you could see that gigahertz signal, and that could actually push you over the edge of your FCC testing as well, especially if you start getting into a band where you're interfering with. So say you look at the 18th harmonic and you're in the 1.8 gigahertz band, and now it's probably unlikely that you would have much energy in that band, but you could start to interfere there, and that's pretty squarely in the LTE range. And so you start to mess with that stuff too. So metal cans can help with clocking, like high-speed clocking, but also more likely in this case, it's RF.
So I've seen cans or something like cans on MPUs. Is that basically why? Or is it
MPUs
in it? Or both?
What's an example MPU? Like a Snapdragon?
Well, I have this really old development board that I found on my desk that has, I think it's a Qualcomm-based single board computer. This is the
that could be
Dragon board 410, and then the Raspberry Pi has a metal thing around it. I wasn't sure if that was a heatsink, a shield, or maybe it's both.
Like on the Pi 5.
Yeah.
I just have one on my desk here. I don't know. My desk is a travesty. Well, the old one doesn't, but I think the new ones are actually, that's a heat sink, the metal on the new ones. So, yeah. This is all to say, probably not going to put this down at first. Obviously, we haven't designed or talked to a shield manufacturer, but it is good to do this because this had a huge impact on the layout, right? So now, whereas I had thought, we had the top layer to route signals directly off these castellated edges. Now, basically, we're saying, oh, well, no, you don't get that anymore because you would run right into a ground path. And so that would be interference there. And so now what you see is really, so I switched this to a 6-layer board. I think I discussed in the last one. So here's the stack up. This is borrowed from this is the stack up of the, that's not right. This is the stack up of one of the 7628 process, 6-layer process from JLC. There is stack up. Where is the, here's the layers now. So now we have top layer mixed, second layer ground, third layer signal, fourth layer mixed. This is actually inverted here. This one is third layer is, oh, that's right, signal. This is really a power plane. So inner 2 is power plane, ground again, and then copper. And the reason for this is that on anytime you want to do a controlled impedance trace, either RF or USB in our case, you usually want to reference a ground plane. You don't have to reference a ground plane. You can reference a power plane if you do good decoupling, but generally it's good to reference ground planes. So now we have below the top layer, the top layer as shown here, and the bottom layer, there is a ground plane. And so all of our constraints are built on that. And now we have controlled impedance traces here. Actually, these need to be rerouted, but these basically are USB traces as well. So if we want to run 50 ohm traces north south here, we can do that because of the ground plane directly below it. Okay, let's delete some stuff. What do you think? Just like that. Now, all this stuff will come back. It's still showing a ton of unrouted stuff, so that makes me think I don't have a layer turned on. Objects. Let's try updating this. Oh, yeah, look at that. It brought it all back. All right. I'm going to have to delete this at the schematic layer. Let me do this off screen. You guys talk for a little bit.
Oh no, I didn't come with material.
Mm.
Dan, I saw
Just
you were soldering
do a little
on LinkedIn.
yes hand.
Yeah, I was desoldering on
Oh, yeah,
LinkedIn. Was on the keyboard I'm working on the RP2040 Pro Micro that it came with. It doesn't line up on the it has an extra row of pins, so it doesn't match the board directly, and or an extra set of pins, I should say. And so there's like multiple different versions of this, and the pinout is different. And basically, depending on which one you have to shift it up or down. And so I was shifted the wrong way for the version that I have, so having to do a little bit of surgery. But yeah, it's a little painful because all like the headers are soldered down and everything. So we'll see how it turns out.
I've seen some nastier surgery for dev boards where these 0.1 pitch connectors are I don't know 30 millimeters long, but if you're off by one, then you like have to create a little jig or use a flat pliers to bend them. So
Yeah.
If you get the footprint wrong, I've seen that. That's pretty nasty.
Yeah. So we'll see. We'll see if it if I can squeeze in the time to get it all off. So
what's the keyboard? Is there a specific vendor?
It's the Korn V3 with the Cherry MX switches. So it's a pretty popular one. It's the same one. I think Mike has the same one. He might have a different version of it. So it's a nice one because the build instructions are really really good. Except for obviously it's they don't determine which microcontroller you have on it, so that's the part where it can get a little tricky about placing it. But other than that, it's been a great experience.
And does it have anything to do with the heavy metal band?
I don't think so. Given the nationality of the person who created it, but maybe it's possible.
I mean, Korn is an international experience.
Yes.
I've actually never seen them live, so I can't say I know much about them. I just thought it was a good joke to fill in the time.
Yeah, no, it's fun.
And we're back.
Nice. We did it.
Yeah. Thank you for giving me a second there. So I just created a new branch just to keep myself a little safe on this repo. So let's start over here. So you guys familiar with the process in KiCad? This is what I probably should have done had I been on top of things. But the first thing you want to do is just make sure everything's hooked up properly, right? So that's called electrical rules checking. That's over here. So we'll go here. And this is probably going to give me a bunch of errors that I don't care about, but you should do it anyways. Usually the best ones that it'll find is like, hey, you have a signal, like the scariest and best errors to find before you go to fab is like, you have a signal that is not connected to anything. And when that happens, that usually means that you've like named something poorly. So I've done it where like I had reset and reset_n, and my stupid brain thought that they were connected, but they were not. This is going to give a bunch of these. So these are different types. I'm going to turn off the warnings here. All right, let's see what's not connected. So things like this, right? So this is basically like, I didn't add a no connect pin to some of these things. So like the coexistence ones, stuff like that.
That's for talking to like a NRF50X device?
That is for controlling the antenna usually. Yeah.
Oh, so yeah. But for like 2.4 coexistence?
It can be 2.4 or it can be GPS. the GPS is actually hooked up here, you see. So basically there's a power thing that it just switches power on or off to the GPS antenna, just routes power through. And then when it's not powered, isn't able to pick anything up there. So this is just turning it when it's in GPS mode, it just turns it on.
Got it. Yep.
Looks like I didn't hook up a bunch of the ESP32 C3 stuff. So I will definitely need to go check that as well. Make sure that I'm not going to have the SPI flash is not going to be attached here. This is actually, even though it's the ESP32 C3, I ended up pulling in the C3 FH4, which is the, this is the built-in memory. Did you guys know that existed?
Oh, is it like their old ESP2? Yeah. ESP8285.
So, no, this is just a SIP basically in the same package.
Yeah, for
So
the
just
classic ESP32, they had one SIP. It was the instead of the ESP8260, it was the ESP32 8285, and so the SPI RAM and flash was all in.
Got it.
But they hadn't made one since. I think
Yeah, so they do.
like
they do make one now, which is nice. Okay, so we got that. Let's see what else. What's that?
Probably saves a lot on space.
Yes, definitely. Let's run this again. My computer is just struggling today. Let's make sure I'm not running any crazy processes other than StreamYard, which is seems okay. All right, so pin not connected. This is aux. These I need to double check on. These are, I actually have the files from the development kit and I need to just double check on that. So I'll definitely check on those off camera because I can't show them on camera. And then these kind of errors here, input power pins not driven by any output power pins. These can be useful, but these are symbol 19. This is marked as an input, but it really should be an output. So I'm going to just ignore PowerPoint's not driven, make those warnings. Same thing here. Okay, so that's good. So basically, I'm going to go double check the DEC0 and the aux pins off camera, and everything else passes on ERC. Luckily, this isn't much of there's not much going on in this design in terms of like connections, right? It all fits on a single page, which is great. One thing I decided not to do is if you look on the edge connector here, there's the power enable DGO4S. And so this is actually a pin on the Elixir that I use to control the power rail to the secondary modem. And I think my questioning was whether or not I was going to put the power switch on board, and then we could actually duplicate we could still use it here and off pin as well. But one of the things one of the questions was whether we should power down the secondary modem using the power rails, right? So you basically use a load switch and you say, when you want to, you just power this thing off, and then it's like hard off. So things like, it would not just be for the Dram 1 where it's controlling the ESP32C3. It's actually also for the BG77 or whatever the secondary modem is in all these cases. So
was there a discussion with Sam about this? Maybe in the Washi
Slashy McWashy
stream,
McWashy,
internal Slack.
Maybe I don't remember.
What was the question?
About like a load switch to shut down the secondary modem.
I don't remember that explicitly coming up.
Yeah.
I'm vaguely remembering a conversation. You know what? It wasn't about this or that. It was when you were designing the new integrated Elixir board.
New integrated Elixir board.
The all-in-one, interposer. Alito? Alito.
Okay. That's a long time ago. That would have been like this December of 23.
I can remember that far back.
Okay.
I don't remember the details of the discussion, but more about that it's useful to have hard switches and firmware. Things like that.
Yeah, I mean, no matter how many, like, so what I've been looking at is, so the ESP32C3 will be programmed with a ESP AT image, basically. And there is a power off mode. And, so I've been doing some research just around like, what is power off mode? Because it's really, it's still sitting there listening. You might have peripherals, whatever. The best way to do it is you just turn it off, right? I mean, like it's pretty hard to get around that unless maybe you have leakage from like a pull-up resistor or something like that. But that adds space and then also complexity as well. So like on the Elixir, for example, even though we have a load switch on there, I actually have jumper, like a 3-pin jumper with to be able to kind of bypass that, because one of the hard things is when you're getting started and booting up new hardware, how do you actually make sure that it's on so that you can actually test that it's there? And so we have a jumper that's kind of in default on state, so that it is on at boot. And then when you've properly programmed your 9160 to control the, that secondary area, then the 9160 is in control. You take off the jumper, and then the 9160 powers it up or down based on what you want it to do. So load switches. So the question was whether or not to do that. I think right now the answer is no. Subject to change.
So then it'd be like the only way to turn it off is to do a deep sleep mode.
Mm-hmm. Yeah, and there are commands. I wonder if I still have that up. I had the C3 AT. Here we go. So I was looking at the AT command set. There we go. It's right there. So basically, deep sleep mode, AT plus GSLP. That's the command you would send to the modem, and it would put itself into sleep until a specific time. So that would be, software control of deep sleep instead of hardware control. There are other sleep modes as well. Is it this one? Yeah, light sleep, wake up. So like things like, say you were using the modem, the ESP32C3 in AT mode as the actual modem, you can actually put it in like the, kind of check the network periodically sort of mode. And that's like light sleep. And these are all, the downside being that you have less control overall because you're in AT mode versus actually programming all of the stuff yourself and like having control of different clocks, trees, and stuff like that. So basically, it's like whatever the AT firmware gives you, that's kind of where you're at. But the deep sleep should be kind of everything off. I think it's just real-time clock. Even the BG77, BG95, that also has like a deep sleep mode that is measured in microamps. But I think for simplicity's sake right now, we'll just leave this otherwise.
One cool thing about the ESP32AT firmware is that it's built in the IDF, and so it's actually pretty common. I've seen a lot of folks on a previous product will write custom AT commands. And they actually make it easy. They have documentation, and so you can like do specific functions or which you can't do pretty much with any other type of AT modem.
Yes, that's right. Yeah, they won't give you the source code to start from. Basically, like you'd have to you probably could go and write your own AT command set and start from scratch, but it's like this is like a project you're saying you could start from in ESP IDF and then add the extra one. Yeah. And the downside, you have to like manage your own. If only we knew of some way to manage firmware, but yeah. I mean, managing that is an extra step then, right? If you have custom.
I think also the
This is the one I was thinking.
NRF9160, if operating in AT mode because it's based off of the NCS, you can also add custom AT commands, or they document and explain you how to do it as like a supported use case. But yeah, it's pretty rare.
I'm gonna be honest. I'm never ever gonna use the 9160 as an AT modem. Like it just seems like, I don't know, making a Porsche into a donkey cart. I don't know, like like in like Back to the Future 3, where they're like pulling DeLorean with like horses. It kind of feels like that. Maybe that's a better example. Yeah.
You're
like
2 for 2 on the analogy train right now.
Great. All right.
It's highly visual.
Yes.
The only case that I could think of is if you have
if you're buying from our friends at what's it called, the module maker.
Oh,
I don't remember the name of the module maker.
Oh yes, I know what you're talking about. No, the use case is if you have if you're using a Cortex M7 kind of application, you're doing vision, display, HMI stuff, and that's your main app. But you also want a M1 to dial out. You could potentially use the 91 as the AT modem.
Yeah, I guess. I didn't see. Sorry, we had a question from Regis. Did you guys see this?
I did not.
Looks like he took over Dan's face. The way that it overlays it. That's great too, because Dan's going to answer this one.
Is there a security test for these devices? Yes, it's a very simple answer. Right now, no. But perhaps in the future. I think there's a variety of different aspects to security of a device that we could talk about. Obviously, like the firmware, the network connection out of it, and then also the hardware security as well. So there's mainly on this stream we're talking about hardware. Which
does he mean these devices, like the ones that I'm designing?
I'm guessing yes. That's what I was implying. Which is why I answered with no.
The most secure thing about these devices is you cannot buy them currently.
Yeah, right.
Couldn't get them if you tried. Yeah, but
I'm quickly looking also obviously there's a lot of engineering and security engineering that goes into the chips we're using. So the 9151 and the ESP32C3. I don't know offhand if Nordic or Espressif has collateral around the security testing they go through, or any certifications that may represent the testing they go through. But that is a class of tests and standards. If I can find anything, I might drop it in, but I don't think I can.
Yeah, you mean like actual like SOC 2 style, or like other certification?
Yeah, well, so for like that secure element you have on there.
Oh, sure.
There's levels of security certification that they have in order to be a trusted secure element. ESIL, I think, is one of them. You could pull up the.
There's also all the PSA certification now.
Yes.
Which I think is potentially most relevant to this question. Very assertive. I think most are like level 1 and 2. A lot of it has to do with like the firmware as well. And I think I can't remember what the distinctions are for the different levels. I'm sure we could pull it up. But part of them involve, having a secure element. The categories are like boot, something about hardware, something about like the application level firmware, that sort of thing. And there's a variety of different ones on there. I'll pull up the PSA docs here real quick.
Just going to quit all of my applications in the background to see if I can possibly get this computer to start playing nicer.
Yeah, so if we jump over here to, let's see. Can y'all see that?
Mm-hmm. Yep.
Yeah, so effectively, like for the different categories, you can go through. So manufacturers, silicon vendors, system software providers, so like Zephyr, for example. And there's a variety of, like I said, different categories, and then there's different levels for each of them. You can go through here and actually check out who is certified and who's partners here. And then all the specifications are open as well. So like the place where we see this most clearly, which is not specifically related to the hardware necessarily, is with the PSA APIs. So you'll see in pretty much every platform now the PSA crypto API, which is basically like an interface for implementation of various cryptographic operations. And so that could be that, like, for instance, on a bunch of the Nordic chips, they're based on ARM cores, and so they have trust zones. So they have secure and non-secure portions of the processor. And so, you can do some operations in the secure part and then have like your application run in the non-secure. In fact, if you actually use Zephyr, if you see that any of the board definitions that are postfixed with _NS, that's basically saying like Zephyr and the application are running in the non-secure space, and then the bootloader, MCU boot in that case, is running in the secure portion. But then there's also like other cryptographic operations you want to do besides boot. So, for example, common one for us is if you're connecting to, over the network somewhere and you want to encrypt communication, you'll likely need some sort of private key to be able to do that. So, for example, which secure element did we end up landing on for this board, Chris?
It's the ATEX 608B.
Gotcha. And that was the same one that was on the Elixir. Is that right?
That's right. Yeah, it's unsupported currently in Zephyr. So this is it's really a future proofing kind of thing.
Yeah,
but in that one, it'll do it'll sign certificate requests. It holds the private key. You never really actually see the private key. It's always, you basically just say, hey, give me a private key, store it in your memory. Don't show it to me, please. And then it always lives there.
Right. And there's like a couple different aspects of support that I think is interesting in Zephyr. So you could have like literal drivers where you're talking in some protocol over to these secure elements. So like I2C or something like that. And so that's one aspect of it. And then another is like integrating with different subsystems. So like, once again, thinking about networking, something I've actually been working on recently is embed TLS, which is very popular. TLS, DTLS library for IoT devices and other types of devices as well. But in version 3, they moved to having PSA crypto support, which is basically saying like, hey, you can provide drivers that offer these different cryptographic functions that we do throughout TLS and DTLS operations. And previously, that looked like you had to have a driver in their old driver model that basically looked like, okay, you have something that can give me a key to use, and embed TLS that would then use that key to do a handshake and negotiate a temporary key for that communication and stuff like that. With moving to the PSA crypto APIs, there's what's called opaque drivers, and opaque drivers are more like what Chris was talking about there, where you can say to an external system, like, hey, sign this with the key rather than give me the key and let me sign it. And so
that was always confusing to me too, because I was like, well, you have this secure element, which is like, unhackable in theory, whatever. Like they do like, chip decapping, trying to extract keys, all the fuzzing and whatever. I'm like, but it's going over I2C. So like you could just look at the I2C traffic. I'm like, what is happening here? But the idea is you never actually see the key because it's always encapsulated in silicon. You're just sending basically like challenges. Is that the right term?
Yeah, I guess like requests, you might say. Yeah. I think the coolest or potentially like most unintuitive, not really unintuitive, but anyway, an interesting thing that these secure elements can do is, obviously at some point you need to do certificate rotation on devices, and that's pretty tricky, right? Because like if you need to be issued a certificate, how are you getting that onto the device without the private key only living in the secure element? And in that case, the private key is generated on the secure element, and then it generates a certificate signing request, which you can then send over the network to get signed by a CA or something like that. And then you have your cert, but your private key actually never left the secure element, which once again is kind of the same concept, but it's like another layer of like, you're actually kind of like rotating your private key in that case.
Yeah. And so it would be like you have a different private key. Like, yeah, because there are 16 slots in the ATEX 608B. I think you basically just say like, give me another one, and then that's when you're like you switch from A to B, and then I think then you get issued a new cert based on the new private key. Maybe?
Yeah, I think that's right. The librarian Chris and I have talked about this a little bit offline for these chips called crypto auth lib, and I think supporting that via embed TLS would actually be the most beneficial for us, which is where I've kind of been looking into. And like, for example, I guess it depends. We would probably be more likely to leverage it via a driver for embed TLS rather than like direct I2C communication via a driver in Zephyr. So anyway, but CryptoAuthLib, for example, could use an I2C device. Actually, CryptoAuthLib does have support for an I2C device. So you can, there's like sort of support, I guess. It depends on how you're trying to use it.
Yeah. Yeah. Okay. That's security.
Right. We answered all questions about security.
We're done with security. It is now a finished topic.
It is secure. Yes. All things are secure. Things that are not certain. I'm not super confident about is this little wiggly worm here. This is the GPS antenna. This is basically the best I could do with GPS antenna. You see that I was doing some mitering of corners, or what do they call it? It's called a fillet. It's fillets. Yes. So I'm doing some fillets around the corners here to, basically get rid of discontinuities again. There are discontinuities here. This would be better if this was the same width as the trace itself, but I think we'll be okay. So now I've deleted all things. I've deleted all non-Dram 1 things. We're down to 2 unrouted. Let's quickly do DRC on this one. I think I've closed enough stuff that this hopefully doesn't drag like crazy. All right, so here we go. We are missing connections between, oh yeah, that's good. That's a good one to know. This one here. So this is, I've also hotkeyed up my entire computer. So, or I changed, I guess, the KeyCAD hotkeys so that I can change from, so if you want to see it happening here, I can change between the different layers with just 1, 2, 3, 4, 5, 6. I basically sound like Mike talking about all the keyboard layers. So it looks like I don't actually have SW clock hooked up. That's bad. So let's do that real quick. Eagle-eyed viewers will note that the layers are actually getting kind of busy here. Also, I don't know if I showed this last time, but we have shove turned on. Have you guys ever seen this in KeyCAD?
No.
This is one of my favorite things.
I can ask. You're just being very casual with your.
Oh yeah, yeah. So the idea being, as you're routing, right? So I basically click X to start routing individual trace. But like right now, I want to go kind of north south here, and you see I have a blue trace in the way. So what I would have had to do in former versions of KeyCAD is actually like go redraw that and then get it out of the way. Now what I do is I just barrel through it, and it's like, oh yeah, I can figure this out for you. And so you can just kind of drag this stuff along and kind of figure out where this can go. And I can do it. So basically I'm going to just do this, go to layer 3, go across like this. It looks like magic, doesn't it? Kind of looks like I know what I'm doing, but I don't.
I remember that being a big thing on Twitter when Shove was introduced.
Yeah, there was a lot of really good demos. Yep. And so now, like, this is kind of what I want it to be, but not like great. So now I can mouse over, hit D to drag, basically. And now I can go and drag stuff around to fit kind of more what I want it to look like. And things that I usually optimize for are if I do want ground planes between stuff, I usually want to have good spacing between different lines here, especially like high speed stuff. So what did I see that one say? There is so this is SW clock. I don't worry about that as much. That is that's the programming clock basically. So like it's kind of like an I2C 4 megahertz programmer for ARM chips. That's fine because it's not actually running, but things like this here. So I have S clock which could be up to 10 megahertz on a SPI setup. So I might want to make that, give that some more space, that sort of thing. And again, this is probably stuff I'm going to do off camera to truly optimize. We're just kind of doing error checking now. And that was not hooked up. So what was the other error? So that was 1. And then unconnected item number 2. This one. Oh yeah, just didn't hook up right here. There we go. Boom, done. All right, good. I know, so easy. All right, only 547 errors, guys. What is happening? That usually says to me that I put in the wrong constraint somewhere, and I've either completely screwed myself for later, or it's still crunching, or I'm about to fix it very quickly. All right, silk screen overlaps. I don't care about those. Those are warnings. All right. Clip by solder mask. All right, so via diameter net. Okay. Net class default minimum diameter of 0.5 millimeters, actual 0.35 diameter. Yeah, so this is in the board settings here. So that's this button up here. And this is constraints. Minimum via diameter is 0.5. But I set it to 0.35 in my net classes, right? So this is basically where I said all my vias are allowed to be 0.2 millimeter holes. This is something I talked about in a previous revision. I said 0.2 millimeter is the smallest, but actually that's not, it is both the smallest and the default 0.2 millimeter via hole, which is small, and then 0.35 millimeter via size. But then I didn't update the constraints here to match that. So, and this is basically the check that happens across the entire design.
What was the other thing that's not a constraint? We just showed a minute ago.
Yeah, so this is it's called net classes. So basically, this is kind of where you see that I had set. So when you are making controlled impedance traces, you're using the thicknesses of the various layers of the PCB to define. So between the thickness between like the top copper and the next layer down, which is going to be ground, that and then the width of the actual trace itself, and then the thickness of the copper, all that stuff kind of adds up to define a size of track. And in this case, 0.2939 millimeter track is going to give us the closest. This is from a PCB calculator from JLC PCB. That's going to be a 50 ohm trace if it has, if it's coplanar, that it has ground on either side of it, and it has ground below it, right? So that's kind of where we live there. And so that's how I chose that. So then I had to go and say, okay, well, some of the lines are going to be 50 ohms, like the ones that are actual RF lines. Everything else is going to have a default. In this case, it's everything else is just default. So anything that's not in this net class assignment is a default. Oh, so actually, this one's also default.
To kind of like simplify my thinking, the net class is literally how the nets are laid out. This is like the default size and whatever, and the constraints is then when you do like a rule checker, it's gonna verify.
Yes, this is basically, the constraints are basically kind of like basically what it's saying is like go to your board manufacturer site, look at the bare minimums, like the minimum sizes, put those in here, and everything's gonna be checked against those. I did not update all of these, so that's why. So like the same thing here. This is also giving an error, surely, because I have it set at 0.3, but I actually have it. I have the default set at so I have the through hole set at 0.2, and I have the via diameter at 0.35. But that was set at higher level, basically of the previous default.
Okay.
So I predict that we're going to be able to look at all these red arrows. That's basically highlighting every via that I have on the board. Let's try and run this again and see how it does. Computer, go! It's not usually this slow. It's because my video is running. And StreamYard is getting very rough these days. I'm not sure what's going on. But you see all the different checks it's due. Oh, I was wrong. It's still throwing a bunch of errors, but a lot fewer, only 193 now. So let's see. Let's turn off warnings. Annular. Okay, so now this is just a different setup. Annular width is 0.1 millimeters, and the actual, given the size difference. So basically the via is 0.2, the annular ring is 0.35. And so basically if you 0.35 minus 0.2 divided by 2 is basically like how much copper is on either side of the hole. And I didn't change that one. So that's the remainder of these errors here. One thing I should really do is go make sure I'm not screwing myself later. I have a window. Yeah. Okay, so this is where you would, it's good to go pick a manufacturer. I chose them for this sort of thing, but I'm going to go for, let's see, traces, solder mask. Is it here? NPH, vias, where are the vias? Via to track. I was doing this off of the thickness tolerance. Hole size, non-plated. These are tolerances. Minimum via hole size / diameter. Via diameter should be 0.1 millimeters larger than via hole size. Okay, so that really should move up. They'll probably give me an error, not an error, they'll probably bounce that back to me or size it up themselves. Yeah, hole size diameter. It says they can do 0.15, 0.25.
We have to bounce to meeting.
Okay.
I'll have to watch the rest of the stream to figure out if you get the errors down.
I mean, I could just go turn those off and try and submit it, but I think generally we could just try and do it otherwise. So yeah, we'll see how it goes. I'm sure it'll be fine.
Cool. This was fun. Thanks for inviting me.
See you, John. All right, so one of the things that's problematic about this is that it's going to, because I have these vias near other stuff, I can go and match the capability, but then it's possible that I might width. Yeah, so this would get rid of it right here. The 0.1 millimeters would get rid of it. Find sizes, net classes. Let's try it and see how it goes. All right, so that'll fix the errors. Now I can go here, say for vias, go to net class. I want to set to the net class rules. All right, let's see how this does. All right, so that just thickened up all the vias there. Now let's try and run DRC. I guess I'm going to have lots of interferences now. Not too bad.
I've got to go grab a cable. I'll be right back.
Okay. So that got rid of the error that that was the error, the size of the via on either side. So now we have a 0.2 millimeter hole with a total 0.4 millimeter width. So the thickness of the via plating should be 0.1 millimeters. All right, well, let's start going through these. So this is, well, that one's not going to work. That's just the true interference right there. All right, so this one is, this is a legacy thing. This is from, oh, Wild Mike appears. Hey, Mike.
Hello. I'm back from lunch. So.
Oh, great. This is, so we're in the middle of DRC right now.
Yeah, yeah.
You just missed John. I don't know if you were.
I was watching the preview, but then when everyone dropped off, I was like, well, Chris can't be lonely. He's got to have someone to talk to.
Yeah, well, I appreciate that. All right, so this one. So let's get rid of this trace first. Already doing better, I think. Let's do this here. 6. Oh. 6.
Oh my gosh. So you're routing 6 layers right now?
Yeah, no big deal. Right?
How many layers are you using for traces?
Only 2, actually.
Okay.
So 2 ground planes, 1 power plane. Oh, sorry, 3 signal planes. But because of the RF shield that we were talking about in the first half, basically you kind of cut off access to all the castellated edges from the top, from this top red layer. So yeah, I'd say like 2.5.
You can do internal routing on that layer?
On this, yeah. So this is the orange one, and Dan, I apologize, we're talking colors here. Orange layer 3. I'm seriously, like, from an accessibility standpoint, it's really tough with PCB stuff because it's like colors are integral, I feel like, to do that sort of thing. Yes. So layer 3, which you can kind of see it switching up here. So 1, 2, 3, 4, 5, 6. Layer 3 is kind of our east-west routing. Layer 6 is kind of our north-south routing, but it also has controlled impedance USB traces here, which are not very well done right now. I need to fix those up. And then layer 1 has some component stuff. Layer 2 is ground for the top side. That's the ground reference for the RF stuff. Layer 3, that's east-west. Layer 4 is power. Layer 5 is ground reference for the bottom layer, and then bottom layer is the north-south. So. Pretty fun, huh? All right. Let's keep going on the errors here. We're getting there. All right, here's an easy one. Courtyards overlap. This basically just means that this component, this is a capacitor, is too close to the 9151. Okay. That was easy. This is clearance violation default 0.127, actual 0.1115, which means usually that means that I've just moved something. Ah, I see. So this is because this little guy is too close to these traces, I think. These are locked traces. I locked the the USB traces. So those are still things that I need to go and reroute.
Did you lock them because they're exactly the same length right now?
I locked them because I wanted to, so when I've been pushing and shoving around, like I talked about earlier, you want to make sure that you can't push critical traces.
Got it.
So you can so basically I just said lock those and they'll stay put as is. Hole clearance violation. Hole clearance 0.25, actual 0.22. Where is it? Sometimes you have to zoom in. This is the USB stuff. I think it's because the 50 ohm must have Huh, that's weird.
When you changed your vias, did the locked traces not change?
Yeah, that's a good point. Yes, probably. That's probably part of it. I just need to rerun these lines anyway, so we might do this last. Let's just go get rid of the other errors first, and then we can do that.
Since you gained a mic, I'm gonna drop off. But thanks as always, Chris.
All right, thanks, Dan. Thanks for being here.
See you, folks.
It's like babysitting the hardware engineer.
I was just thinking that. I was like,
Since Chris can't
someone's
hurt
got to
himself,
watch Chris. He'll
since
order
Chris can't hurt
500 of
himself,
these.
or yeah, exactly. Exactly. All right, what's this one? This is the coexistence. So this is basically because these kind of errors here, clearance violations. This usually is just because a trace got moved or got moved.
Yeah.
Oh, actually, that's probably because I upsized it and it was just a little bit too close.
Right.
This is
Oofed
same
up.
thing here. This one you can just kind of drag around until it's not green anymore. Boy, it likes being green though.
You got to switch the way that it's bending that upper left leg.
Well, that actually, yeah, that actually is right. It's because it wasn't. So you can do in KiCad, you can do something called control and click, and it'll basically let you place a trace even though it's violating DRC. The easier thing to do usually is to remove one of the violating traces and then
Redraw it.
redraw it. Yep,
So the arrows don't go away until you run the DRC again?
that's right. There is I think you can select it. It's very awkward to do that though. And I think you can
don't do
clear
it for my account.
Yeah. All right. And then you can see that some of these things deleted item. You see that as you fix things, usually it says deleted item as well because the violation goes away. Hole clearance. This is an easy one. All right. So we're just going to run that again, see if it starts to get rid of some arrows. Oh, that was just the zone fill rather.
Oh, 10 errors you got rid of. Nice.
Yeah, not bad. All right, so this one is drilled holes too close to other hole. Probably just need to move these. Clearance violation, ground, probably just that. It's on the right layer. Frontside copper, backside copper. 6. Okay, this is the USB. This one is the hole clearance. So let's just drag this guy around. This one, probably just this ground here.
So you just use a regular mouse for this, Chris?
Yep. My wrist is very sore. Actually, I've been doing a bunch of layouts. So
I was going to say, I wondered.
Yeah. My setup has been very poor lately. Though, I've been elevated, so I'd bend. So it's. I need to. I've gotten a little bit better, but honestly, whenever I'm doing a bunch of layout design work, it usually starts to get sore. So.
Yeah, I wondered if you had I wondered if you had a mouse that had assignable buttons, because it seems like there's a lot of really common key and click sort of situations.
Yeah, that's a good idea. Actually, I do have 2 thumb buttons, but I didn't think to assign those. How many buttons do some mouses have?
I don't know, but I do have the thumb buttons, and I use them for forward and backward on the browser. I really like that.
Yeah,
for some reason.
I've never used those. All right, so let's just highlight these. So if you hit U twice, you highlight the whole net. Hit Shift, hit U again, highlight the whole net. You can see the whole thing going up there.
Cool.
And what I'm going to do first is right click. I can just hit L, but I'll just show it here. Locking. I'm going to unlock, and then I'm going to delete. And what this does basically, Yeah, I mean, basically, the only reason I really had it locked in there is because I wanted to save the lane there.
Right.
So
Okay.
I'm going to follow that same pathway. You can kind of see there's like a kind of a runway here.
Yeah.
I'm actually going to get rid of this one. And let's just try and route it again. I bet this will get rid of it. So I'm going to do, I got rid of my hotkey for the differential pair. That's usually 6, but since this is a 6-layer board, my 6 has now become.
Oh, yeah.
Thing. All right, via.
Oh, and it shoves for you. Nice.
It does, yeah. Now, I'm going to probably do a little bit more cleanup there. I would like to, because this is a controlled impedance pathway here, I would like to have pretty solid grounds on either side. You can kind of start to see where the math starts choking.
Oh, yeah. Is it like lagging on your computer?
Well, it basically just kind of like says, I don't know what to do next, right? So it's doing math as it goes. And when you give it like I went too far on these two, right? So I'm going to delete these two and just give it a smaller jiggy jog. That's a technical term.
Jiggy jog. Can you start from the other end?
Yes, you can. Yep. That's a good point. But this should be sufficient here. And then coming in for a landing here. Okay, didn't like that. So this is tough because this is a non-standard spacing between these two pins.
Ah, right.
Let's see if we start here.
Oh, cool.
We can line it up.
Or
see, like right now it's trying to like make the turn, and it can't like figure out how to make the turn. There we go. And see, like this is just a little bit off.
Yeah.
So I think I'll do what Mike said and delete these two. Start from this side. Route, differential pair. You get a little bit more leeway over here.
Maybe.
Yeah. Delete these. Route.
I feel like this happens to me. Like I get the grid off by just a little bit, and then I can never connect stuff straight anymore.
Mm-hmm. Get this guy out of here. This really shouldn't have been.
Ick.
Okay, 6. Route.
No. It says no. There you go. Touchdown.
Yeah. And so now, like, you see how this ground is kind of not here now? It's not complete, rather.
Right.
Actually, I'm not even sure why this has a via. Is this 1, 2, 3? This doesn't even need a via. So we'll just get rid of this. That's nice. This one does need a via. Bounce it to the other side. And what I'm trying to do here is just kind of clear out so it has a nice solid ground plane around it.
So you're trying to make it so nothing crosses the ground layer?
What I'm trying to do is make it so that it's so that it experiences. So like if you imagine like you're a signal going down these two traces, right? Your calculated impedance between the two controlled impedance lines, between the 90 ohm differential pair here, is dependent upon the thickness of your material you're on top of. So like you basically have like a dielectric layer between the copper on the top and then the ground plane below it. So there's like basically like a capacitor between the two. And then also now there's like a ground on either side. And so if you're kind of going down this track and you have these high frequency signals going, and then you're halfway down the track and there's a big chunk of copper missing now because of a cutout, whatever, it'll probably be fine. But it's a discontinuity that now the impedance is basically changed a little bit. And so it's kind of like what it sees. I know this is like anthropomorphizing electronics is kind of silly, but what it sees is different. And so I just try and minimize that. So like just that little cutout there, now it sees copper and specifically ground copper. And so, kind of going down this track now, let's just look at the zones here. We can make this more opaque, right? So now right here, this is like a little bump out here. Now that would actually do it, which is good. And it's going to redraw and actually close this up. The downside is what I did on the top layer. So actually I just bumped the vias over a little bit. Right. So now there's a 50 ohm up on the top layer. This is probably okay because it still has ground here. The reason I have vias all along this pathway is because you want a really, really low impedance path along, so that the ground is really grounded, really low impedance.
Is that an antenna?
This is a 50 ohm. This is the cellular line for the LTE antenna. Yeah. And so this is a 50 ohm pathway going out to the UFL. And so same kind of things happening here where you have a ground, you have a coplanar ground with the coaxial line. And you want it to be very, very low impedance. So I guess if you look here, this 3.3 is kind of problematic regardless of where it is. I think that might be the best we can do right now.
Got to move the capacitor.
Got to move the capacitor. What capacitor?
What is that part?
So this is the GPS switch.
Oh,
so this is the power going into the GPS switch here.
Got it.
So that's the coexistence control signal. All right, so I'm actually less worried about I almost would. I think this will be fine. So as is it is, but now we have a controlled impedance going all the way down to here to these vias, and then it switches to the top layer. I would say now, if we can get this. Ooh, still had that selected. Sorry, this is super jumpy right now. If we can get this via, so we can have a little bit of ground in here, that would be best, but not required.
There you go. Yeah. Well, kind of,
yeah.
Yeah.
I don't know if we're going to be able to get it. That might work. There we go.
Yay!
Yeah, so I'd say that's probably the best we're going to do there. So let's see what I just moved. That just bumped some of the layer 3 stuff around.
Okay, but those differential pairs are not necessarily the same length, are they?
Correct. And you can do tuning if you'd like. So
probably doesn't matter on USB. I don't even know.
This stuff is, so first off, this is low speed. This is USB 2.0. And this is, it's going through a card edge or like a castellated edge.
Right.
So like, that's already not great. So like, it's probably, so if you have really bad discontinuities in your controlled impedance differential pairs, what you're going to do is you're going to start to see like the eye diagram close down a little bit and like have like worse signal integrity. Worse signal integrity will be like kind of like noisier signals for USB. So at high speeds, you'll start to see like more noise on that. But USB is just like super resilient. So like it's probably going to be okay. We could try, we go to route, tune length of a differential pair.
I'm mostly asking because I've never done it. And so I want to see how you do it.
Yeah.
Whoa.
Yeah, this is wild.
And then now you're your nice ground plane's all screwed up again.
Yeah, that's what I'm not going to do this. But like this is like if you wanted to, you could start doing that sort of thing. But really, in this case, it would be more about the skew as well, right? So like if you had different lengths on either one, you might want to do just one side. I think I have not done this in KiCad. Let's see. Looks like it's saying that we're okay. Current skew. I'm sure there's different lengths here, but I honestly am not sure what I'm doing at this point.
Okay.
Yeah, I should look into that. I'm pretty happy with just having, having the coplanar ground around this thing. I should lock these traces again now that we've done this. Oop, I still have the tool selected. Hit escape. Oh, this is not what I want.
You needed those extra mouse buttons, Chris.
I think I still have the skew turned on, maybe. Okay. And let's hit L. So now those are locked. So now if I try and move them around, yeah, it says locked. Great. Okay, let's go back. How are we doing on time? We are rapidly approaching the 90-minute mark, which is my spiritual stopping point.
No errors. Woohoo!
Oh, I'm not sure it's done running. Is it? Oh, okay. These are all silk screens. Thickness. Via is not connected to. Okay, so this one's probably a good one too. This is a straggler, looks like. Track is an unconnected end. These are good ones to. This is true cleanup here.
This is like a vestigial trace that didn't go anywhere.
That's right, exactly. Yep. And this is just the. This is based on the thickness of the text because I used a non-KiCad font. There's sometimes like small artifacts, so that's fine. I'm keeping that. I think the processors can handle it. They often when you send this into a board house too, they'll, if you send them a silk screen they can't do, they'll either modify it or tell you. Silk screen clip by solder mask. What is this? Oh, I see. This is the outline for the UFL. Same thing. Oops. Same thing.
Can you mark these as like approved?
Yeah. So you can do ignore all silk screen clip by solder mask. And now you can turn exclusions on or off now. Silk screen overlap. Oh, this is just because of where this one. So this is that little part here. So it has a marker for pin 1, so that if an assembler was doing that sort of thing. So if you want to change this, we can hit E, edit the part. Go in here, edit the footprint. This is just for this board, not the library. Let's do something like that. There we go. Fix that one.
That wasn't bad.
Yeah. Silk screen overlap. This one we can just move this down here. Thickness. Ignore. Deleted. Run DRC. Does not match library copy. Oh yeah, okay. That makes sense too because I just changed that. So I think we got them all, Mike.
Woohoo!
All right, let's take a look at the design here. All right, Mike, now a question for you, oh Git, master of Git. I have all this stuff in a different branch, but yes. I have the main design that has like everything in it.
Yeah.
What do I do? Do I just split it out to its own repo, you think, or save it as a branch, and then just like kind of leave it behind?
I'm confused. Don't you just want to open a pull request?
Well, I deleted all the other boards that were on here. So Dram 1, 2, 3, 4, 5, 6. That's what I did at the beginning of this. So I got rid of everything else just to make.
I mean, do you want a standalone repo for this?
I think so. I don't know. I kind of wanted like the shared, parentage of the Dram module and stuff like that. I guess that could just be the library footprints and stuff like that. But
you could fork the repo, and then in the fork, you could set this branch up as the main.
Oh, that's a good idea. So then it still has the reference of the old stuff, but
yeah, you can still like pull stuff in from the upstream if you wanted to, but otherwise, this becomes a standalone.
Okay. Good stuff. Good stuff. All right, so I am going to. How much time do we have left? We have 5 minutes. Let's take it to the house. Let's generate some Gerbers. Dram hardware output. Gerber. Open. Yes. All right, so I'm going to generate all of these layers here. I want to we're good there. Plot. I'm going to generate drill files. I usually put PTH and NPTH in the same file, which shouldn't matter for here because I don't think I have any NPTH. All right, let's see what this looks like now. Okay, so now we're going to go to Gerber Viewer. Open files. Oh, that's the job file. That's fine. Okay, so now we can just kind of look through the various files here. So this is just the drills. This is backside copper. Now let's start from the top. So front side copper. So this is the 9151. This is the ESP32C3. These are the various controlled impedance traces here. This is power. This is the ATEC. This is the memory. Layer 2 is ground top. That's what that looks like. This is no, that's not the layer. Inner layer 1. So this is the east-west traces here. It's kind of hard to see. So there's those. It's kind of hard to see with there are the green stuff, the green ones underneath. We can just look. Hide all but active. There we go.
Yeah, that's much better.
Okay. Let's do layer 2. This should just be the power layer. And you could see the only thing that's really, so there's some, you wouldn't really see much cut out here because it's really just anything shown is really the exclusion zones for ground. But you see over here, this is the 2 pads where power comes in. So that goes right into that layer. Let's do layer bottom ground, which would be pretty solid. Yeah, nothing fancy happening there. And then bottom copper. And so we see there's the USB traces that we just did.
Oh, cool.
Yeah.
Yeah, it's way more obvious now about that.
Yeah,
isolation.
that helps.
Yeah.
Let's see, silk screen.
Mm-hmm. Oh, can you label every pin for me before you send that silk screen in?
This is a ongoing drama between Mike and myself. So this is actually going to be, this will be interesting. So we'll keep the top copper layer on, but then let's turn on the top solder mask, because this is going to show now the outline of the shield. Except,
or not. You got to reorganize them.
Because the organizer, yeah.
Yeah.
And move it up. Move current layer up. Oy.
Convenient.
Yeah. Modern, nothing says modern like a Gerber viewer.
That is looking good now. Look at that.
Yeah. And you can see this one here too. So this is the ground pin for this part, but it's actually just connected directly to the ground. So this is grounded as well. This top layer is ground, is assigned to ground net. So that's also grounded. It does make me wonder if we should be putting more just ground vias to tie the top layer in a little bit better. Because this is currently depending on, so like this one here, you see this opening up here, these are all grounded, right? So this is basically the ground for the 9151. The top left corner is grounded. These pads are also grounded. They basically, it's like you have the sheet of copper, and then you just open up the solder mask and say, okay, that's connected there. Same with these over here, but kind of in between, there's a bunch of stuff that's not really, I guess these are grounded. Yeah. But the real thing we wanted to do is, connect to the large sheet of ground, which is right below it. So I might put some more vias in before sending this off. And then let's look at the...
Did you judge that just by looking at it? You're like, oh, there's large distances where there are no vias.
Yeah, that's right. So sorry that colors keep changing, but look at this right here, right? So like this whole layer is ground. It's like an exposed ground for the shield. But like, where is the closest ground connection to the layer below it, right? We would need to have the drills turned on. And then
there's some, right?
I guess that is one there. So this is one, that's one. Layer, top ground. Yeah, I guess you're right. There are some here. So like that's definitely one, and that's one, and that's one, that's one. So yeah, there are some. I guess I should have turned on the drills. But still, like, just to have a low impedance, so this is a great example of like having the inner layer connected to the top layer, right? But that is less the case over here. So if we do have space, might as well drop some extra vias to tie the grounds together, sort of thing.
And KiCad won't do that for you?
I mean, I can do it quite easily. So it's literally like, if I wanted to do that, I just go here, drop a via, ground, 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 ground. If there's any kind of like interference, then it's like, okay, what do you want it to be? Or not interference, but like which net do you want it to be?
Yeah, I'm just surprised it doesn't have an option like add vias every, whatever square millimeters.
Yeah, you could do that. So there is a so you can go like select this. This is the old way that I used to do it. And I think there's a replicate tools. There is a way to like replicate every polygon, create array. There it is. Where'd it go? Create from selection, create array. So I could do that, right? And that's basically did like every 5 millimeters. But like, look at all these interferences that already happened because of it.
Yeah. Oh, okay. So it's not doing it smartly. It's just doing it.
Yeah.
Yeah.
So it's better to like, now what I did is I turned on the opacity for all these zones. So you can see the traces, but now what I can do is say like, oh, well, I wouldn't want to have a trace on top of, I wouldn't want to have a via, like a ground tie via in between or on top of a trace, but in between, no problem, right? And I know there's going to be like, even like clearances, I can just eyeball the clearances and say like, oh, I don't want it to be too close. But anywhere there's space, I could just drop one like that.
And you're not paying by via or anything like that, are you?
If you did like an insane, like this is just not that dense of a design, to be honest. So if you did, there are limits in terms of like density, but I'm not even close. So
because every time you click, a little drill is going to have to go and drill, right?
That's right. And yeah, not a sizable. This is a 0.2 millimeter drill as well. So like, yeah. JLC, if you're watching, well, you're the ones who wanted to start a board house, and they do great. All the board houses.
They must own a carbide company.
They literally have like counters on how many drills they can do, and then they just like eject them and then just move on to the next thing. Yeah. So it's pretty wild. This is the other one where like near the edge here, I want to do some edge ones.
And what happens if you don't do this?
Well, if you think about like return paths, so say you had like a slow return current here, it might just have to like find a different path that's a little bit longer. And in doing so, it might decide that the fastest way to do that is to start radiating. And so in terms of like having a good non-radiating design where it's not supposed to be radiating, right? You might get yourself into more trouble when you get towards times for FCC testing and stuff like that.
So yeah, if you don't pay for the extra vias now, you'll pay for it in the anechoic chamber.
Yeah, that's a good way to say it. And this is just truly scattershot too. So it's not like this is scientific in the slightest, right? So actually these are probably fine up here. See these are all ground pads on the top corners of the castellated edges as well, which means we're also going to connect that to whatever the board is below it. So, all right, I think we've
now it looks fancy.
Swiss cheesed it. The downside to doing this sort of thing too is that when you go to revise the board, now you have a bunch of vias in the way, right? So that aren't like critical, right? So you might want to go and just get rid of them then. So I've had that happen before. These are all slow signals. Those are fine. All right. I think this is more than enough hardware streaming. Do we have any other questions in the chat? I don't think we do. Yeah. Mike, thank you for showing up. I think it's time for me to go off camera and go buy one of these boards. What do you think?
That's right. Yeah. All right. Well, you're going to pick it up too, right? So you're going to
fly to China.
Yeah.
Probably not. But I think I do have a couple more checks I need to go do on the reference design, the design, what does DK stand for? Design kit? No.
Development kit.
Development kit. Yeah, I got to double check the development kit files that were sent to me. So, all right. Thanks for being here. Thanks everyone for watching. We'll be back next week. Actually, I have a different project for next week. We'll see how that goes. I think here's a preview. Here's a preview of the potentially for next week. It's all I'll show. Skinny Al Udell. All right. Thanks for being here, Mike. And thanks everybody for watching.